So we can talk about R vector space and C vector space just to underline what field name we are using. So for the real and the complex numbers, we talk about that as a name, a field. And so we can use either of the two. Okay, and like I say, what is really most important for these vectors is to understand the examples. And maybe one of the best known and best understood examples of real on R vector space is R to the n. And these consist of vectors b and R to the n is an n tuple. And addition, if we also have w in R to the n. So if you have v and w in R to the n, then the sum is defined simply to be coordinate-wise sum. Like this. And maybe I will say alpha times v is then alpha v1 alpha vn. So this, I guess, is well known. And then we have something that we also have seen before, but it is certainly not something you have seen in the algebra. Namely, if you take a vector space then we can associate to this, for example, the space L1 of mu to be all integrable functions. And this is an R vector space. So this is one of the things we saw when we discussed L1, that this is actually a vector space over the real numbers. And we can maybe remind ourselves that if we have two functions, then u plus v is simply the function which is given like this. And alpha times u is given like this. So this is another example of an R vector space that we should be quite interested in also, or very interested in. Then we have also, again, if we have a vector space, we can also, oh yeah, maybe I should say, so we also have, for every time we have p between 1 and infinity, the space LP of u, and this consists of all functions u which are measurable, and I underline what is the sigma algebra, and u goes from x to the real numbers, to the real vector space, such that the integral u to the power of absolute value to the power of p, then u is finite. So this is something we discussed last week. And we also have that these are vector spaces. Then one thing I will just briefly mention here, and then I will come back to it, that you also was told about in chapter 12, is that again, say you have p between 1 and infinity, then you can associate the space LP of u, and this consists of equivalence classes. So let me just say like this, it is LP of mu modulo some equivalence relation, and it consists of equivalence classes of functions. and then we just, here I'll come back to more detail later, then we just say that here what you do is you identify functions which are equal almost everywhere. So if you have u and v in a p of mu, then if they are equal mu almost everywhere, that would be the same thing as saying that they are identified in LP. And this can be really convenient because sometimes we don't like, these functions somehow should be absolutely equal. And the way to make them absolutely equal is to pass from curly LP to this LP space. And let me just here say that LP of mu is also an R vector space. Okay, and so another example, if now we pass to complex spaces, then the easiest example is V equals C to the n. This is a C vector space. And again, I will not be repeating it. It's exactly the same as this example, except that all entries here are now complex numbers. You can add them together in the same way as you can multiply with my complex numbers. So I guess if you have seen these, such an example, and it is first linear or vector spaces over complex numbers in linear algebra. Maybe that's how you have seen it. But the rules are precisely the same, so I will not mention it any further here. Another example we could consider would be the space, say, of continuous functions, say, from some interval into the complex numbers. This is a C vector space. And the idea is, again, if you have two functions that you get for the f of g, then you can add them and say also maybe have a complex number alpha. Then the sum of the two functions is again pointwise sum. And alpha times f you multiply again pointwise by alpha. So you somehow get the idea that what we are after here is we're really more interested in this kind of space and VLP spaces. This is the kind of vector spaces that we are primarily interested in. Okay, so so after all what we are about talk about is inner product space, and so far I only talked about vector spaces. So now let us define what is an inner product space. And if you look at the book, then I do things in a slightly different order. What the book does very quickly is it discusses how to define these spaces here for complex, for functions that have complex values. And this I will do a little bit later. So let me first do this. So V is a K vector space. So K is either the reals of the complex numbers. Then we say an inner product or it's also called a scalar product, scalar product. That is a function or a map that goes from V cross V into K, denoted by brackets. So we use these square brackets. I want to either use soft brackets or square brackets or hot. And this is the notation we are using in this course. I think it is a good one too. And they satisfy some actions. And the actions are, I believe, the first one here. SP, I guess, stands for scalar products. And then we phrase it slightly differently, emphasizingly before. For all vectors, we have V inner product V is a positive number. And moreover, V inner product V is 0 if and only if V itself is 0. So the inner product of the vector with itself is a positive number, and it is only 0 if V itself is 0. That is the first rule. The second rule says that if I have two vectors, then if I take the inner product V and W and I do it in the opposite order, well, I guess that what you have seen, if you think about touch products and real inner products, you have been taught that these are equal. If you use complex numbers, it turns out you don't want them to be equal. You want this to be the complex conjugate of this. And let me possibly actually remind you about some things about complex numbers. So this is about reminder about C. If I have a Z, a complex number, then I can write Z as alpha plus I times beta. Alpha and beta are real numbers. I guess this is well known. You've seen this before. The number alpha is the real part of Z, and it can be written 1/2 Z plus zeta. I will tell you what that is. And beta is the imaginary part of Z. That can be written as 1/2 times pi. Z minus Z bar, and Z bar is defined to be alpha minus I times beta. So if you only know this, then you can define Z bar, and then you can resolve what the real and imaginary part is by comparison. So we use quite a few facts about complex numbers, and I will try to remind you about both of them. So this is what we're doing here. We are keeping the real value, and we are replacing the imaginary value by minus the imaginary value. So this is the symmetry, and then finally we have linearity. That if we have three vectors in V, if we have two numbers, real or complex, then we can form alpha U plus beta B times W, and that is then the same as alpha UW plus beta BW. And this is saying this is linearity. And this was actually called symmetry. This formula. Okay, so you see that what SP3 says is that the inner product is linear in the first variable. So this is what an inner product is, and so we should see lots of examples, but before I talk about the examples, I want to mention some properties. I guess that some of these properties I will mention now are also things you have seen before, and my guess is that you in linear algebra have seen inner product spaces for the real numbers, and probably also for the complex numbers, but maybe not that carefully. So some comments are due. If you look at SP2, when k is a real number, so the symmetry, that simply reads, that becomes the following, that VW is equal to WV. And what we're using here is the fact that if, we can write it here, that Z is a real number, if and only if it is equal to its own complex category. So if, so what I'm saying here is that if we have a real vector space, then these actually are real numbers, and then taking the complex conjugate doesn't do anything. It's only for complex numbers, taking the complex conjugate does anything. So that's worthwhile mentioning. And then about SP1. Then a problem we have to think about is what does it mean? I guess if you have a real number, then a real number is positive, something we understand. A real number is greater than the zero, we understand what that means. But what does it mean that a complex number is positive? Do you know? Is minus square root is I, for example, is that a positive number? And the answer is it is not. So we should maybe, if you haven't seen it before, so Z is a complex number, then we say that Z is positive if and only if Z is a real number and it is positive as a real number. So that is what it means to be positive for a complex number. So if you have the complex plane, these are the reals, these are the imaginaries, so this is complex numbers, then the positive ones don't have that much, so maybe take the blue. So the positive, these are the numbers which are positive. So these are the okay, so that is how that should be interpreted. And then we have something about SP3. That we, strangely enough, only talk about linearity in the first variable, but what about the other variable? So SP3, and maybe I can just finish that by saying that this means that that is good like this, it's a positive real number. That's emphasized. So we could take an SP3 prime. That would say the following. Suppose we have 3 vectors and 2 scalars. So then the following holds. If we take W inner product alpha U plus beta V, this is equal to alpha complex conjugated beta complex conjugated, we take out like this. So in other words, if we take the inner product and consider the linearity in the second variable, we don't quite get linearity, we get linearity up to complex conjugating the numbers alpha and beta. So in other words, if we want to take out a complex number alpha from the second variable, we have to complex conjugate it. And this is a consequence of the action. So let us just prove why this is the case. So here is how we do it. Just to see how it follows. So what we do is if we just look at the actions, then all we know is how linearity behaves in the first variable. So we would like to put this over to the first variable, and this we can do by using SP2. So using SP2, we can interchange. We use symmetry, but then we have to complex conjugate. And then we can use linearity SP3 and get what is in here is alpha u inner product W plus beta v inner product W, and then the complex conjugate of x. Then we need another fact about complex numbers. Taking complex conjugation behaves very nicely. So here's that. Another fact. If I take two complex numbers, say set and then u, and I complex conjugate them, then I add them. So the sum, the complex conjugate of the sum is the sum of the complex conjugate, and similarly the product. So we have these nice formulas. Actually, another fact we also have is that z times c complex conjugate is absolute value of c squared, which by definition is alpha squared plus beta squared, where alpha and beta are here. So we will use many things about complex numbers, but that means that if I look at this expression, I can take complex conjugate on each summand and afterwards on each factor. So this is the same as, put it here, alpha complex conjugate uw complex conjugate to beta complex conjugate vw complex conjugate. And alpha complex conjugate at p, but then I can use SP3 again and turn it around. Beta complex conjugate at p, and I turn this around. That is. So hence now I prove this back here. So really what you should notice is the way we use complex numbers. I think this is what might be new here. Okay. Then we have an important inequality Uge6A. Let me see, that's a number, so I better copy it. Then 2.3, 20.3. And that says that if I have two vectors v and w in v, and V is in a product space. So by an inner product space, I simply mean a vector space that has an inner product. A vector space with an inner product. But then I can take the inner product of V and W, I can take the absolute value and square it, and it turns out that is the same as taking inner product of V by itself and inner product of W by itself. Notice, by the way, that these are positive numbers. So what we have on the right-hand side is a product of two positive numbers. This is often a complex number, but then we take the absolute value and it becomes positive. So we have this important inequality, and I will not prove it. It has been, I think it has been proven in the algebra. Is that correct? Have you seen it? Which is what in the algebra? No, you have. You have not seen it. Now we have seen it, and I will prove something for you today, but this I have decided not to prove. It is not completely easy to prove, I have to say. You really have to make some manipulation, and oftentimes you prove it using something with a polynomial of degree 2 that has no roots, and then you use the discriminant. Whichever way you do it, you have to apply some small trick. I will rewrite this shortly in a way that you may be more familiar to you. Otherwise, I will just ask you to take it for granted. Then we get to this naturally leads to the next definition. I hope you have seen it in the algebra also. That is, where do I have it? Yeah. It is not written as a definition in the book. But let me do it more formally here. Suppose this is an inner product space. IPS, I call it inner product space. Then we can define a function, a map, and I call it, I use the normal symbols for the map, and this is a map that goes from V into the positive real number. And we define it by the following formula. If V belongs to V, then the norm, or whatever we call it, is defined to be V inner product V to the 1/2. And we should note that V inner product V is a positive real number. Hence, its square root is defined and belongs here. It's one of these things that you should know that you cannot take the square root of all numbers. You can take a square root of a positive number. If you try to take the square root of a non-positive number, you get into problems. It can somehow be done, but you have a choice between two options. So it is not uniquely defined. But for positive numbers, it is uniquely defined as a positive number. So we can take the square root of this positive number, and this we define to be normal V. And this letter is, or this symbol is well used because, as the next result will tell us, this is in fact normal. So let us see. How this goes. So that is a lemma for 20.3. So it says that the map mean that's a norm space? Well, it means that this is a norm. And what does it mean that this is a norm? That means that there are some actions which are satisfied, and let us write them down. That is, we have the following are satisfied. The first condition is the first norm condition, says that for all V in V, the norm of V should be a positive number, and moreover, the norm of V is 0 if and only if V itself is a specific vector. So the only vector that has norm 0 is 0 itself. Then it says that alpha times, okay, if for all V in V and for all scalars alpha, we have that the norm of alpha times V is active value of alpha times the norm of V. And then 3 says that whenever we have two vectors, the famous triangle inequality holds. So the norm of V plus the W is less than norm of V plus norm of W. And I think that how does it go if you have vectors, if this is V and this is W, then this is V plus W. So the triangle inequality says that if you have a triangle now, this has a right angle here, but it doesn't matter. If you have any triangle, then the sum of two sides is always greater than the last side. That's a known fact. Okay, so what we have to do is to show that the norm defined above satisfies these actions, provided that it comes from a number. So let us just convince ourselves about this. Could I ask, have you seen this in any algebra? You have seen it, yeah. Nonetheless, let us take this off. So let me, nonetheless, quickly go through these things. I can put something here. For N1, the first part is here. We already know that norm is a positive number. We have remarked that already. So let us see. V is 0. That is the same thing as saying that V inner product V to 1/2 is 0. This is the definition of the norm. And if a number is 0, that is the same thing as saying its square is 0. And by definition of the inner product, that is the same as saying V is 6. So this proves N1. Let us look at N2. That is a little bit more interesting. In particular, the complex case. So let us try to compute this, and oftentimes it is easier to compute the square. So let's try to compute the square. This is the same as alpha V inner product alpha V. Then we can move this one out, and this figure is done like this. Alpha, we have linearity in the first variable. Then I want to move this one out. And this I can do, but then I have to complex conjugate because this is the second variable. Okay, now I have alpha times alpha complex conjugated, and then you see from this formula, this is the same as Cauchy-Schwarz inequality. So what we do is we take V plus W and we square it. It is much easier to compute the square of the norm because the square of the norm satisfies this relation. Then we don't have to take square roots. Okay, now what we do is we use that the inner product is additive in both variables. So let us do it step by step and say, okay, take additivity in the first variable. So this is additivity of inner product in the first variable, then we take additivity in the second variable. So these two, so this quantity becomes this quantity, and this becomes what I'm writing here. And this, by the way, going from here to here, that should remind you a lot of taking a plus b squared. That is a squared plus b squared plus 2ab. The only thing is, so this is a squared, this is b squared, but 2ab somehow became this. And so let us see what we have. V, this we can write as normal v squared. So this I keep for now. And this I actually would like to reverse. And I take complex conjugate, and this is the normal W here. Okay. Maybe I could use this and continue here. So it's a little bit more complicated. So now I keep the first two terms, or the first and last term, those I'm quite happy about. And then I can say that this is a complex number plus the complex conjugate of that number. And I think we have that somewhere. Right? So if you take any complex number and you actually this complex conjugate, you get, and if you divide by 2, then you get the real value. If you don't divide by 2, you get 2 times the real value. So this is 2 times the real value of the inner product W. Okay, then we need another fact. And where can I put that? Put it here. So again, if I have Z written as alpha plus I beta, with alpha and beta being numbers, then absolute value of alpha is less than absolute value of Z, and absolute value of beta is less than absolute value of Z. And this actually follows from the fact, I think I wrote down the absolute value somewhere. Oh yeah, here it is. So the absolute value squared is alpha squared plus beta squared. And using this, it is quite easy to see the results. So what I'm going to use now is I'm going to say this is less equal to V squared plus W squared, and then plus 2 times absolute value the inner product. And then we use Cauchy-Schwarz. But then actually I would also like to rewrite Cauchy-Schwarz. So if I use now that V inner product V is the norm of V squared, and W inner product W is the norm of W squared, then Cauchy-Schwarz can be written the following way: V inner product W absolute value less than norm of V times norm of W. And maybe this is a more familiar way of expressing Cauchy-Schwarz. Maybe you've seen this. But you see it is exactly the same as this. I just take the square root of both sides. So then we get this formulation here. Okay, and now, I use, say this is dot 2 times V times W, and then this is equal to actually V plus W, the whole thing squared, and then this proves the same, what we are after. This quantity is this